All right, sorry about that. My machine crashed. So today we'll start on the network layer. There's quite a bit to talk about in the network layer, but why don't we start with sort of the end host experience, and then we'll dig into various kinds of routing and how it works in the middle of the network. Maybe I had a nice picture, see if I can dig it up again. There it is. So we can start with this. It's actually from the textbook. So the role of the network layer. So here we have a couple of end systems right here and there. So the network layer has implementations all over the network, and that's unique for the network layer, right? The links above, the layers above are only on the end hosts, the applications, and the transport layer implementation. The network layer is what connects everything together, and then we have the data link layer, or just the link layer, which creates little local networks. Right? You can do an office or perhaps a campus with this, but it's one kind of protocol, and the network layer is what kind of puts them all together. That's why we call it the internet, the inter-network protocol. It's the protocol that ties together a whole bunch of smaller networks. And then the physical layer is virtually always just one link between two hosts. Right, so how do we get it all to fit together? All right, so why don't we start with just the protocol header? We've looked at those before, so when we dig into that detail first, just to see how, let's do it in IPv4. How a packet what it looks like when it leaves the machine. Oh, here it is. Very good. Right. So an IPv4 header, this is what comes before the transport layer header, right? But after the link layer header, Ethernet or Wi-Fi, which we'll see later on. And it says, where is this packet supposed to go in the whole world, right? That's your source IP address, destination IP address. In IPv4, it's 32 bits. And where's it coming from? Our source IP, another 32 bits. And then a few other things that are somewhat important. Right? There's a length of the packet, handy. The protocol that says what's coming after. Right? You basically have to do this. One way or another, you have to say like how we should interpret the rest of the packet. How does that work in the transport layer? How do we say how to interpret the rest of the packet in that? Yeah.
Look at the window size to see.
The window size, no. So what I'm saying is, maybe repeat the question, is how do we know from when we receive something from TCP? How do we know how to interpret the rest, whatever's after the TCP header? There's some payload. Some application payload after it. How does the machine know how to interpret that stuff when it arrives? Yeah.
I mean, it has to have a common protocol, or has to follow the common protocol between who it's receiving it from.
Exactly, but how do we know like what protocol that is?
They tell us in the handshake.
Not really.
I mean, I guess, could you like parse it and if it makes sense or something?
How would you know?
Yeah. The port says what protocol does the end host talk, right? You connect to this machine at port 80, and now we have this assumption that a web server will be responding to us. So we're sort of multiplexing between application level protocols using a port number. it's a weird way to think about it because we have all these different programs, right? If you think about every program as independent, then the program only speaks one protocol, so who cares, right? But from the operating system's point of view, this is one big machine and it's running the kernel and a bunch of plugins. Those are the programs. How do we know which plugin to run? That's the protocol. That's the port for a transport layer. In IP, it needs to know like, oh, which other part of the kernel should be handling this packet as it comes in, and that is the protocol. So you could think of that as how should we interpret the payload, whatever comes after this header, or maybe we think of it as like which part of my code should I kind of condition off, to branch off to deal with the rest of the header, deal with the rest of the packet. There's something similar in the Ethernet header that also says which protocol comes next, and usually you'll see a IP there, but not always. Okay, what else is in here that's important? The version is relatively good, right? Version 4 or 6, and for the rest, I think we don't need to worry too much about them. A checksum. I think that's the same as in TCP, if I remember correctly. Yeah, so you just add them up, unfortunately. And there's a few other facilities that IP provides that we try not to use too much. One is this fragmentation. So you send a large packet, it can actually be chopped up into pieces along the way. Let's ignore that for now. Yeah.
Are all these fields related to the network layer?
Yes, IP is the network layer. Right. So the internet protocol is what the network layer talks. You could imagine inventing another network layer, but I don't think it's happening in the next 100 years. Right? Just because we're stuck with a billion machines doing this now. So let's just do that. Now, IPv6 is used relatively frequently these days as well. Why don't we take a quick look at that as well? In fact, I just took a look. I was doing some weird network thing at home, and something didn't work the way I thought it would, and it was because my machine was using IPv6, which was kind of a surprise. Let's see what that looks like. Yeah, okay, so in IPv6 it's basically the same thing. I wish we had the same format. Okay, it's a little better. They eliminated some of the kind of leftover things that nobody uses, but really we have a version, we have a flow label. Yeah, that's new. That says that's for load balancing and for sort of fairness. We can skip that for now. The most important pieces are the source address and destination address, much longer. And other than that, traffic class, we have that in IPv4 as well. It's not really used much. It's this one here. It says something about, oh, this is a bulk download, right? Versus this is a Skype call. So a router could potentially make a decision like, okay, maybe I'll prioritize the Skype call packets because I know there won't be many, but it's important that they make it in time versus the bulk download. But there isn't really a good standard for this. So this is something that you might see within one provider, like T-Mobile. They might put a label like this on packets, and you might get nice prioritization within the network, but across all of the internet, there isn't really an agreement on how one should prioritize these things, or even verify that it is the kind of packet that you say it is, so on. Okay, so basically that's all you get. You, well, as a network layer implementer now, right, we get an incoming packet. It looks like this. The only thing that we're really interested in is the destination IP address. That's what we're kind of have to try to figure out where to send the packet from only that. All right, so IP IPv4 or IPv6 header, specify a destination address. The address has some kind of structure. You could call it a prefix structured address, perhaps. Addresses with a common prefix may be co-located. Right, so it's not the case that every address that starts with a 0 are next to each other, right? But every address that starts with a long prefix, even like that, they're pretty much in the same place. This would be at UIC. So there isn't a hard and fast rule for how many of these digits that belong together in a group. Instead, there's sort of an arbitrary grouping based on what's called a mask, a net mask. So we describe this as /16. You may have seen this. So we're saying the first 16 bits say something about group membership called a subnet. Subnets based on IP prefixes. All right, so the last bit here says how many bits identify the network. All right, so this 16, that's bit, nice, yeah. Number. So here we're saying the remaining 16 bits of this address, they don't identify a network, they identify a host, a machine within the network. So how many machines could we have in this UIC subnet? Two? Well, cubed. Wow.
Squared. I can't. We don't remember how long that. Is it squared?
Let's see. What
I'm just thinking.
what was the answer? 256
Squared.
square? Yeah. Okay. So IP addresses have 4. We usually write them like this. All right. So there's 4 of those. Each one of these is a decimal number between 0 and 255. So it's actually 4 bytes, right? And you could write them as like 4 of these hexadecimal pairs as well, right? But so here we're saying 16 bits is what identifies a host. 16 bits, that's 2 to the power of 16 different combinations. So for 16 bits, we have up to 60,536 hosts, right? There are a couple of addresses within a subnet that don't act quite the same way. You're not supposed to use those for hosts. There's the 0th address that identifies the subnet, the network itself. It's not something we use for a machine. Yeah.
Sorry, I'm a bit confused. Would 24 be the largest subnet, or would 8 be the largest subnet?
There.
/24 or /8.
Oh, there is no such limitation. So you could have a 131 /
So that would be 24.
This is an 8.
Okay, so the 24 would be the smaller one because that's how many bytes are the heading at the beginning.
Right. So this number identifies how many bits identify the network itself. So this is the 131 network.
Yeah.
That makes sense. Yeah. But you could also go, actually I don't know that you can go smaller than 8. I don't think I've seen that. But we could have a, could look like this. But it could also look like 25. Let's see, does this? Yeah, that's fine. So now these are two different networks. This one is contained in that, right? But this is the one that has a 0 at that highest order bit among the hosts. So it starts getting a little hard to reason about with these particular numbers. Actually, it's fine. It's like this. All right. There we go. All right. So this network here has 256 addresses in it. This subnet has 256 addresses in it, but then it can be further subdivided into these two subnets if you like. All right. So it's up to the administrator of a particular subnet to decide like how I want to divide up my IP addresses, and we don't need to worry too much about that at the moment. But basically, we divide up the internet into these pieces that we call subnets, and at least in principle, each subnet could be an individual destination. It could be anywhere in the internet. So you could actually, and now we're getting a little bit ahead of ourselves, but you could say that all of this is UIC. In fact, all of this is UIC except for this address, which is in, say, Taiwan. All right. Anyway, we divide up the 4 billion addresses available into little groups, and we treat those as individual destinations. And we'll see how we route that in a little bit. Okay. Within one of those subnets, there's a couple of special addresses. There's a 0, which we don't use, and I don't quite know why. It's supposed to identify the subnet, but I've never seen that address actually used for anything useful. I've asked others, but nobody had a good answer. And then there's the, so all zeros identifies the network, all ones is the broadcast address sent to all hosts in the network. So if you want to ask the local network something like, oh, have you seen the printer, let's say. Like, where's the printer? Then you would send that to this kind of pretend IP address with the all ones at the end, and then it's up to the network layer to decide for this underlying link, how do I affect a broadcast to everyone in the subnet? Usually you can just kind of send it out on the radio or on a shared link and it'll be fine. Sometimes you might have to send to every host you know about on the network. Okay, let's get back to this thing. I think there was something more interesting in here. Special use addresses. Let's not worry about that. Okay. Okay, nice. Leave that alone. All right. So that's pretty much the interface that the network layer presents to the transport layer. The transport layer wants to deliver something to an end host. And so now we have to specify an IP address, or maybe to a group of end hosts. We could do that with the broadcast address. But all we get to do as a transport layer is to just give you one packet, and it gets delivered to the other end. All right. So how do we get from a bunch of these disconnected machines, all talking different underlying link layer protocols, to one unified network that where you can reach anyone from anywhere else? It looks something like this. Let's see. All right. So we might have an Ethernet network over here, and Ethernet machines talking Ethernet. So let's not have the machines in there. And then we might have over here, we have a Wi-Fi network. And here we have a cellular, say a CDMA network. And in here, you identify this is the end hosts by phone number. It's kind of getting a bit of an archaic way to describe this, because these days the CDMA sort of all they want to do is deliver IP. That's all right. Here we have end hosts identified by MAC address. Oh, and good. And here we have a single little serial modem connected. So that's dial-up PC. All right, that connects to, let's connect it to over on this side. And here we have some optical. All right. Probably be more like that. All right. Definitely not this one. Okay, so we put it together a packet over here in our modem connected PC. We say we want to send it to some IP address, some destination IP address. And from here, with a dial-up, there isn't really a further address. We've connected to some machine that has another modem at the office, let's say. You call up over this thing and you have a direct connection. It looks like a serial port, only it kind of translates over the phone network. So you just send your IP packet without any further headers. You send it over this phone network. It arrives at some PC over here, and it sees, oh, here's an IP packet. Where do I want to send it? Okay, so it actually needs to go out. We know there's, within this Ethernet network, here's my PC. Okay, let me put PC. There's a PC. And within the Ethernet network, we can send packets based on a MAC address. So we have a link layer that delivers this service. Any MAC address you want that's on this network, we will deliver it. Right. For now, we've abstracted away the link layer. Maybe I should grow this a little bit. All right, so this PC receives a packet, and it says, okay, it needs to go out on the internet. I know we only have one router. For now, keep this simple. We only have one machine that is connected to the internet. That's called a router. So let me send this packet to the router. Make this a little bigger. Okay, so I prefix this packet with a router MAC address and the rest of the link layer protocol, and then I give it to my network interface on the PC. And the link layer API basically is give me a header with the destination address that's on this Ethernet network, and the packet will be delivered. Okay, so I put in the right stuff in it. It gets sent over to another PC over here. Actually, we can call that a router. That's the same thing. A PC and a router is no difference, only a router has more network interfaces and probably a smaller CPU. Okay, so the router sees this, and now it sees, okay, that was for me. So we delete this, and we look at the destination IP address, and okay, it's for the internet. And I know that all of my internet routes, because we're keeping it simple so far, are in this direction. So now I'm actually connected here over let's say this is a cable modem sort of thing. So now we put the cable modem link layer header, and I forget the name of that. Let's see. Come on. Has a nice name. Oh, DocSys is the one I was thinking of. I don't know if it's still that, but let's say we call this the DocSys header. So this router says it removes its Ethernet address, which was on there. It says, okay, I know I need to send it to the next hop here, the end of the Comcast network. There's some receiver end there that takes all my packets and does the right thing. Okay, so I put on the right header so that machine gets it. I sent it over here, and now the receiving end at Comcast sees, okay, that was for me. All right, so that this keeps going. Now we probably have another Ethernet. Next, hop MAC address. Most of the hops will be Ethernet addresses. We don't get to see them at the end host, right? Because we delete, like we send it over here, now we get to the next hop, we delete the previous MAC address, put on a new link layer header, and so on, across many hops over here, and then eventually, maybe we make it over, let's make it, and this cellular isn't such a good example. Anyway, so at some point, it makes it over to our Wi-Fi router, and we call it a router, but they're really very weak machines. They really shouldn't be called routers, because usually they just have one incoming port, internet, and then a radio, and potentially it has a little switch built in as well. Talk about the difference between switches and routers later, but they really don't do much. Okay, so it receives the Wi-Fi router MAC address, and then finally it puts on a, so now it sees, okay, this network, it actually made it all the way to the right subnet. This Wi-Fi router is the owner of the destination subnet. So it sees, okay, I need to send this to one of the machines on this network. I recognize the IP address. I know its MAC layer, address, in this case a Wi-Fi Ethernet address. And so I'll put that on there and deliver it to the end. How do we discover which is the correct MAC address for a given IP? We'll find out in a later lecture. It's called ARP, Address Resolution Protocol. Wi-Fi header with final hop MAC address. Right? And it's sent over the Wi-Fi radio, and finally it's received on the other end. So that's sort of the steps along the way, and that's routing in what we call the data plane. So a packet is received, and we immediately, based on the IP address, we know where to send it next. There's no computation really done. We look up just for this prefix, it needs to go over there, and that's pretty much instantaneous. So that's the data plane part of routing. The interesting part of routing is the control plane. That's where we figure out what should be the next step for any given IP prefix or for any given subnet. And we can't afford to do that for every packet. if we were to do that for every packet, there would be a whole lot of work, potentially sending many packets just to figure it out, and that would get very expensive. So that's sort of done proactively. Every router already knows for every destination where it should send the packet next, and it on the fly basically looks it up for any incoming packet. Okay, so before we dig into the specifics of like routing in this enormous network, we need to figure out some of the little abstract details of how the control plane of routing works. How do you figure out which is the appropriate next hop for a given destination? It's pretty easy when you're this router. This router knows the subnet of this. This has some IP subnet, right? So it'll know that, oh, if it's that IP subnet, it's for me. We keep it. And if it's not, then I send it out on the internet. So as long as the network is shaped like a tree, much like we did in the previous homework, as long as it's shaped like a tree, you either give it to someone in your network, maybe one of your children. Right? If you were to divide up this part into more pieces, right, you could maybe have some child subnets inside of you. And then for anything else, you hand it up to the root. But much of the internet, at least the core internet, doesn't look like that. It looks more like a proper graph. So, in fact, I may have a pre-drawn picture. Let me see if I can find that. That would be handy. Maybe. Ah, perfect. Found it. Okay. Okay, so here's a more generic graph. So let's forget about IP addresses for a bit, right? It's good to kind of have that in the back of your head, but in this case, one of these letters refers to an IP subnet. Like, that's a destination. As long as you get to the subnet, you don't need to worry about the individual machines inside of it. Then we know that we can get to the destination just asking the link layer to deliver it for us once we got into the right subnet. So now we just have these unique identifiers, letters, and we need to determine how do we get from A to G. And each one of these circles is an individual machine. These lines are an individual cable. And so there's no broadcast domain here. There's no way to just send a packet to everyone. These are just actual cables. So if you want to send a packet from here to there, you better send it to B first, and then somehow have something figured out so that B forwards it to E. Right? That's what we're looking at. So an easy way to do routing, let's say we want to send a packet from A to G. It'd be easy to do sort of data plane routing if you could say, you say C, H, G, right? So A here specifies the whole thing. So it says, okay, I want to send from A to G. Let me just, in the packet, specify what's the next hop. So I say, okay, let's send it to C. C gets it. C sees, I'm supposed to send it to H. That's really easy, right? You just look it up. You know which one to send it to next, and then finally you arrive at G. Great. Unfortunately, A doesn't have any information about the network yet, so we can't do that. This is called source routing. And if we have a complete picture of the network, which you could have it pre-configured, right? If it's a small network, the administrator could just say all of these links exist, and the machine could easily compute it. Or if it's a really small network, the administrator could even say, use this specific route, right? And then you would know. Unfortunately, there's also none of this in the IP header that we saw, at least. There is actually an option in the, at least in the protocol, you can in principle say, I want you to go through these hops, but this is disabled in all the routers out there. It's an old it was an old idea, it was cool, and then they realized, oh, it's actually really dangerous, let's not do that. In the beginning, there weren't so many malicious actors on the internet because there were only a few kind of military or university nodes, and that was it. Okay, so how do we get from A to G? First of all, we need to learn something about the network. There's a couple of standard designs of routing that I think span most of what's going on. So one of them is called distance vector routing. Right. And the other one is called link state routing. So with distance vector routing, the idea is everyone knows how far it is from everyone else. So you keep a vector of distances from you to everyone else. And by sending that to your neighbors a few times, you can eventually converge on a consistent view where everyone has the right distances. And if you know your distance and your neighbor's distance to a destination, then we can route. Let's see how that works. And then with link state routing, instead of distance to everyone, you actually know all the links that exist in the whole network. And if you know all the links, then we can compute the route locally. Like on one machine, you can say, okay, I'm going to go this exact route. And if everyone has the same picture of the network, everyone would compute the same shortest path. And so everyone locally computes what's the right path, and that'll work fine too. So we'll have to look at both of these in some detail, but let's take a simple example. And we'll only deal with one destination for now, but this works the same for all destinations. So in this case, the destination is G. So how do we teach the network about how do we get to G? Well, the first thing is for G to announce its presence. So G can send a message out over these links. I wonder if I can make them. I won't make any arrows for now. So G would send over these three links. That's the only thing G has access to. And remember, there's no other protocol yet. There's no other information or anything in the network, so we have to start somewhere. Where do we start? Well, G will say, I am G. I am distance 0 away from G. So now these guys, if we keep things simple, we assume that the cost of a link is 1. We're only interested in the number of hops. You could say, try to have some other cost. You could say, oh, this is a really low bandwidth link, so I should have a higher cost, so it's less likely you will want to use this one. There's a high latency link and so on. But for now, let's minimize hop count. This is sort of the standard metric out there. Okay, so we've announced this, and now what? So for now, there's only one destination. That's why we can have it in a circle here. If we have many destinations, it's harder to draw. So we'll do that next time. Okay, so now, what do these guys do? So this one, let's do that. It can say, I am 1 hop away from G. Right? And it can send that then over all of its links. It could potentially even be a little clever and not send this one, because it got it from G, right? So what's the point? So it won't send that back. All right, and so now this node gets it received this message. It heard about G for the first time, so now it knows that, oh, I'm 2 hops away from G. And this one, what about this one? Any ideas?
Doesn't update because.
It doesn't update it, right? We want to keep it the minimum number of hops. That's the whole point here. So we just kind of ignore that message. All right, and this continues. Now, okay, so now we can see what happens here. We do a few iterations here. Let me do that quickly. All right, and from here, we'll get a 2, and here there will be a 3, so we'll pick a 2. All right, so now finally, A receives, from this one it's received a 5, from these two it's received a 2. So now that A wants to deliver a message to G, what does it do? Well, it picks the minimum of these. Well, now there's 2 minima, so let me just pick one of them. We send our message, a message for G. All right, we send it to one of them, I'll send it over here. This node D doesn't need to know anything more about the packet than where it's going. It doesn't need to know how long it's been traveling or sort of what was the other intents of A here with this packet. It just needs to see, okay, it's going to G. So what do? I pick the minimum next hop to get toward G and send it over there, and then one more transmission. Right. So once we've done this routing exchange about the information about the distance to G, now all of these nodes in the network know the shortest path to G. That's the whole point of routing. We want to send it along the shortest path, or sometimes the least cost path. Okay, so if we want to generalize this, right, we end up with something more like a table. And so every node will send like A, B, C, D, E, right, and its distance, 0, 1, 1, 1, 2, perhaps, right. And maybe we'll go like this. So for every sort of turn of this execution of this protocol, I send everything I know, like all my distances. I send it to my neighbors. My neighbors take the minimum of their previous values and my values, and to update their table. And I guess they also need to remember what is their, internally they have to remember what is their next hop, right? So I need to know for G, my next hop that I decided on was this one. Okay, so that's all great. Now, what happens if we lose a link? Let's try this. So we used to go along this route, and so this is a big deal in networks, right? The network is actually dynamic. You would think that internet isn't that dynamic. It's mostly dynamic within one link layer, but every now and then, and it's probably because the network is large, it's probably several times a second, let's say, somewhere in the world, one of these important links go down. So let's bring this link down. Okay, so now you would hope at least that these two can discover that the link is down. Let's say the link layer tells us this. It doesn't have to be like this. It could also be that we periodically send these messages, and if I don't receive a periodic message, I interpret that as the link being down. But let's say I do. So now what do I do? What do I do over here? I notice my link is down. Yeah?
You look at your vector and you check all your neighbors who have a connection to G and update your distance.
Mm-hmm. Right. So this guy is announcing a 2. This guy is announcing a 2, and this one's announcing a 1. So I'll stick with the 1. Right. Okay. So my new next hop, and now maybe I should put some arrows. Wrong way. So my new next hop is over there. Very good. And so now I have to update this. And now, well, everything else maybe stays the same because it used to be we had arrows going this way. All right, I should have probably put the arrows in. Sort of indicating the next hops that we used to have. And we can stick with, in fact, we can't quite stick with it. This one's going to have to update to a 3. Okay, let's bring down one more link before we have 1 more minute to go. So let's just kill this one too. And now what? Now it gets a little weird. So now, I guess this one sees that it lost the link, and this one's broadcasting at 2, and that one's broadcasting at 2. So I'll just pick one of them as my next hop. Right? Maybe I'll go with that one. Right? Okay, that's my next hop. Right, very good. Right, so then my cost is 3. All right, so the cost went up here. It's a 3, so I should probably increase my cost, right? This was my next hop, but that's no good anymore. I mean, I'm going to go with a smaller cost. So that's my next hop. All right. Okay, so now I have a cost of 3. Very good. On this side, it looks like I'm going to have to go with this one. So my cost is 4. Unfortunately, now this guy is announcing 3. All right. And so this is problematic for a little while. But it keeps going up and up, and this one also keeps going up. Fortunately, at some point we reach like 6 and 7, let's say, and now this one is 6 away. Right? This is stable here. So we know this is 6 hops away. And these can't go any here. If they keep going around, they're going to go higher and higher. So now this is going to pick 7, pick this as a next hop. It's the wrong way. Right. So eventually now this becomes an 8. And possibly that would be a 9. Then if we were to have the same path, we wouldn't. I guess we would reverse this and so on. So eventually with this distance vector scheme, we do reach a new shortest path to the destination. Okay. Simple example of distance vector routing. We'll do lots of other examples next time. Okay. In preparation for the midterm, I suggest reading the transport layer chapter, TCP. We're not going to have the network layer on the midterm. Right. So we'll leave that for later on. But up to the transport layer, definitely well worth reading up on.